Assalamu alaikum to you all. Welcome to this course, the design and analysis of algorithms. Before we start our first lecture, we're going to go through the syllabus of the course. I have already opened the syllabus here. The first part of it is obvious, basically the course code, the course title, my contact details, and so on. Probably the important parts are the objective of the course, the textbook that we're going to use, the grading scheme, the course learning outcomes, which actually are similar to the course objectives, just putting them in from student point of view rather than from the teacher's perspective. And then the scheduling of the course in terms of topics and assessments. We take on the objectives and the course learning outcome first. Well, the objective can be summarized into 2 points basically, although they are stated here in several points. There are 2 main objectives really of the course. One is to teach students how to design efficient algorithms using different algorithm design techniques. And the second part is to learn how to analyze the efficiency of algorithms, both in terms of time and in terms of space. Alright, those are the main objectives. The rest are actually just going into detail about the different topics that will be taught, but these are the real objectives. And therefore, in terms of our course learning outcomes, we have 3 of them here. Okay, course learning outcomes, of course, are the things that you are expected to know or learn by the end of the course, things that you should be able to do by the end of the course. You should be able to describe the basic concepts of algorithms and complexity classes. You should be able to apply algorithm design techniques that you learn through the course, such as divide and conquer, greedy approach, and dynamic programming, to solve problems. And lastly, you should be able to compare, both in terms of time and space, the complexity between algorithms, how one algorithm is better than another, both in terms of time and space. These are the things we hope you will be able to do by the end of the course. Alright. Now let's look at the textbook. The textbook we shall be using is actually one of the most popular textbooks on algorithms that is used by many universities in different countries around the world. I have a picture of the cover page here. It is called Introduction to Algorithms by Thomas Corman, Child Lizerson, Ronald Revest, and Clifford Stein. As a matter of fact, as you will see on the internet, the book is normally shortened as CLRS, based on the 4 authors that authored this book. We're going to be using the 3rd edition of the book. I'm sure you all have access to the online version in your Blackboard account. Okay. I'll talk more about the book maybe when we look at the schedule of the course, the scheduling of the topics. Let's go back to the syllabus. The next important aspect of the syllabus, which probably is more important to you, is how you're going to be assessed. Okay, now the assessment is very similar to what you have seen from other courses. Basically, there are going to be 2 quizzes of 10% each. There will be assignments. However, although in the system you will see them as 2 assignments, I normally break them into 4 assignments of 5 marks each, and I normally give them before each of the other major assessments. So the first assignment will be before quiz 1, the second one will be before midterm, the third one will be before quiz 2, and the final one will be before the final exam. But the idea usually is so that in addition to getting the marks that you are supposed to get in the assignment, it should also prepare you for the quizzes and for exams. Yeah, so I normally break it into 4. So we're going to have 4 assignments of 5 marks each, consisting of the total will be 20%. Okay, and then of course there will be the midterm exam and the final exam. As usual, 20% for the midterm, and final will have 40%, for a total of 100%. I'm sure you know the rules regarding attendance. I don't have to emphasize anything about that. The final aspect of the syllabus is the scheduling of the topics as well as the assessments. You may not understand the topics, so I'm not going to go through them one by one, but the syllabus is going to be there on the blackboard. You can always refer to it to see where we are, and in case you want to learn more from the book, you can also see which chapter those topics are going to be from. Okay. You will see that the book actually is a very big book, very bulky, about 35 chapters. However, we're not going to cover obviously all the 35 chapters. If you check this, we're going to cover only about 9 chapters of the book. Even the 9 chapters, not all the sections in each chapter. The scheduling here tells you exactly which sections of the chapters are we concentrating on. Alright? Yeah. So you will come to know most of this as we go along. But perhaps the important thing to note are the times for the quizzes. Quiz 1 is going to be at the beginning of week 5. The midterm, of course, usually is in week 8. And quiz 2 will be somewhere around the end of week 12. And then, of course, the final exam will be at the end of the course. So this is about the syllabus. I normally stop here if it were a traditional class to ask if there are questions. But we shall discuss if you have any concern in our regular meetings. I will explain probably more things in the meetings. Alright, so that's about the syllabus. Now let's move on to our first lecture. Okay, so here is the outline of this introductory lecture. First, we're going to remind ourselves, I'm sure you know what is an algorithm, but we shall remind ourselves about what is an algorithm. Then we look at pseudocode, because we're going to be representing our algorithms not using programming language like Java, but using pseudocode. So what kind of pseudocode do we use to represent algorithms? This is what we're going to discuss. And then we talk briefly about the different ways to prove the correctness of an algorithm, because actually we are concerned with three things, although I mentioned two things in the objectives: being able to design algorithms and then being able to analyze them. We are also concerned about correctness of algorithms. So when you design an algorithm, in addition to analyzing the algorithm to see how efficient it is, we first want to be sure whether the algorithm is actually correct. Does it do what it is supposed to do? So there are a number of ways to prove the correctness of an algorithm, and we're going to go through some of them in this introductory lecture. We shall see, of course, many examples as we go through the course. Then we will spend some time discussing about RAM. RAM is a model of a fictional computer that we're going to use, that we're going to base our analysis of algorithm on. Okay, the RAM is a short name for random access machine. Then we will start by looking at how to actually analyze simple algorithms. What are the basic steps to follow in analyzing simple algorithms? One of the examples we will see is the insertion sort. Alright, so that's the list of topics for this lecture. We start with the first one. What is an algorithm? Now, algorithm actually is normally applied to computational problems. So before we remind ourselves what is an algorithm, let us define what are computational problems. And here it says a computational problem is a mathematical problem specified by an input and output relationship. Okay, we will see a number of examples of this kind of computational problem in a moment. So an algorithm basically is a computational procedure for solving a computational problem. So you have a computational problem that you want to solve. An algorithm will give you a procedure, or if you like, a step-by-step process of how to actually solve this computational problem. This diagram explains the relationship. As we said, a computational problem usually involves some input, some process, and then some output. Now, the algorithm is somewhere here in the middle. It is the one that will actually take this input, process it step by step to produce the output. Yeah, so the algorithm gives you the step-by-step procedure for actually solving the computational problem. And I'm sure we have seen many algorithms in our previous courses, particularly the data structure course. We saw several algorithms, so it's not new. These are examples of computational problems, just so that you don't think they are something extraordinary. Sorting could be a computational problem where you receive a sequence of data items, which could be numbers, could be text, could be whatever, but we want to sort it in some particular order. If it is numbers, usually you want to sort them in increasing order or decreasing order. So there is an input, which is the data that is not sorted, and then there is an output, which is the sorted data. And the problem here, the computational problem here, is how do you actually move from this unsorted data to sorted data. Okay, another example is searching. Shortest path problem, which I'm sure you are familiar with. We all remember the Dishgra's shortest path algorithm. minimum spanning tree, traveling salesman problem, solving a Sudoku game, knapsack problem. You may not be familiar with this one. We shall come to it later in the course. Even chess, deciding what move to make, is an example of a computational problem. Towers of Hanoi is another example. Spell checking. Most of our modern word processors like Microsoft Word, they have a tool that will help you to check for the spelling of your text. So how do you go about that? It's also an example of computational problem. So there are many computational problems that will normally require an algorithm to be able to solve them. And being able to come up with that algorithm as step one, being able to check that the algorithm is correct as step two, and finally being able to check the efficiency of the algorithm both in terms of time and space are the three main things that we are concerned in this course. Yeah, actually this is what I'm going to say in this slide. What are the basic issues of interest to us in this course? So the first one, as I said, is how to design algorithms. And the second one is how to prove that the algorithm that we design is correct. Okay, does it terminate? Does it go into an infinite loop? Okay, if it terminates, does it actually do what it's supposed to do? Does it solve the problem as we expect it to do? Okay, so these 2 points are of concern to us as well. Making sure that the algorithm that we design is in fact doing what it is supposed to do. And the final aspect that is of interest to us is the efficiency of the algorithm. And this can be in terms of the computational cost, that is how much time does it take to actually execute this algorithm. Okay, and how much memory does it cost, and how do these efficiencies of both space and time, how do they vary as we increase the input size? Okay, so these are the real issues that we are concerned in this course. Now, many of the algorithms that we shall encounter are not new algorithms. In fact, they have been implemented a long time ago, but we still need to go through them to make sure as computer science students you understand those algorithms. So the question is, why are we interested in learning these well-known algorithms? Okay, yeah, so this is what I'm saying here, that most of the algorithms and data structures that we will discuss have been around for a while, and in fact they have been implemented in many programming languages as libraries, so that you can just invoke them if you need to use them in your application. But we still need to understand those algorithms. So the question is, why are we interested? Well, there are two main reasons, which I characterize here as theoretical, and the second one coming up is practical. Theoretically, as a computer science student, algorithms is the core of your major. So it is very important that you are well grounded in algorithms, even those that are well known. Okay, if you graduate as a computer science student, everybody expects that you know those algorithms. This is one aspect. The second aspect, which I call practical importance, is that so that you know what is possible and what is not possible. So even though this algorithm have been designed by somebody else, and in fact they have been implemented already in programming languages, you still need to know them so that you know what is possible. If you have a problem and you don't need to start from the scratch to design an algorithm for that problem if one already exists. So how do you know that one exists if you don't study the algorithms? This is the point. Okay, the other aspect of it is through this course we will learn that certain algorithms so far have proved to be impossible to implement, at least in an efficient manner. So when you encounter such kind of problems, you should know that you shouldn't probably waste your time trying to find efficient algorithm for solving those kind of problems. Yeah, so those are the point. And of course, another point is that learning these different algorithms will serve as a framework for solving or for coming up with algorithms for newer problems. Obviously, the problems that were already solved, they have been solved, but you're going to encounter newer problems in your career. So by learning the previous algorithms, it will guide you as to how to design the algorithms for newer problems. Okay, so that is why we need to learn even the already known algorithms. And the last one is we should be able to know the right algorithm to use for a particular problem. There may be several algorithms to solve a particular task. For example, if you are implementing an algorithm for a device that has little memory, then you wouldn't want to use an algorithm that takes a lot of memory, even if that algorithm is very fast. Alright, you may want to compromise and go for one that is a little slower but doesn't use a lot of memory, because your device on which you're going to implement your algorithm doesn't have enough memory, and so on. So if you don't study all these different algorithms, how will you be able to know which one is the right one to use for the particular problem you are solving? Alright, so that's where we are interested. Now there are many algorithm design strategies. I have listed some of them here. You have what is called brute force. This is the worst kind of algorithm that you can come up with. Basically the one that tries to solve a problem using trial and error by trying to check all possibilities. Sometimes that is the best you can do. If you cannot come up with a better algorithm, probably your only option is to do the brute force method. Yeah, so there are many problems that so far they don't have any algorithm, any efficient algorithm, and the best we can do is to follow the brute force. There is a technique called divide and conquer, another one called decrease and conquer, or transform and conquer. We shall concentrate on the first one, divide and conquer. Okay. Another type of design technique is called greedy approach. Dynamic programming is another one. Backtracking, which I'm sure we mentioned in the data structure course. We briefly talk about backtracking. And branch and bound. So these are all different kinds of algorithm design techniques. But the one I highlighted in blue here, divide and conquer, greedy, and dynamic programming, are really the three main design techniques that we shall focus on in this course. Okay, now let's focus our attention to pseudocode. How do we actually represent our algorithms using pseudocode? Okay, so it says here that in this course, pseudocode is used to represent algorithms. This will look very similar to common programming languages such as C, C++, Java, maybe Python, and so on. But actually they are not, the pseudocode is not a programming language. To explain this better, let's take an example or two examples. And this is our first example. I call it Mystery 1 because usually in a traditional class I ask my students to try to see if they can understand what this algorithm is doing before I tell them what exactly it is doing. Okay, so as you can see here, the algorithm is represented here in terms of a routine or a procedure or a function which receives an input A. So here A actually is an array. So it receives an array. And it takes the first element in the array, save it in a variable key. Then it starts a loop starting from index 2 until a.length. So from 2 to the end of the array. For each value I, or for each index I, it will check the element at that index I and see, is it greater than our key? If it is greater, then we're going to update key to be the element at that index. And then go back and change the index to 3. If the element at 3 is greater, we're going to update. If it is not greater, we're going to keep the key as the current value. We don't change it. And so on. So at the end of this loop, we return the final value of key. So the question is, what is this algorithm doing? Obviously, if you are careful enough, you'll see that this algorithm is trying to find the maximum value in an array. Find max. So it assumes the first element is the max, and then it goes through the rest of the elements. If it finds anyone that is bigger than the current max, it will update the current max to be that element, and so on. So this is our example 1. We'll take a summary of the point to notes in a moment. But before that, let's look at the second example. So here, Mystery 2, perhaps this is a little less clear to explain what it is doing. It takes an array A again, and then it goes into a loop, starting from 1 until the floor of a.length over 2. I hope you still remember what is a floor and what is a ceiling of a fraction. Okay, so we have floor and we have ceiling. Let's say our length is 5. So 5 over 2 is basically going to be 2.5. So the floor of 2.5 is 2, whereas the ceiling of 5 over 2 is 3. Okay, this is the idea. So this algorithm goes from 1 until the floor. So if you have 5 elements, let's write some random values. Okay, let's say you have 2, 7, 1, 3, 9. Suppose you have this 5 values in an array. Let's see what this algorithm is trying to do. So it says for each element I, where I goes from 1 to 2 in this case, because the size is 5, we're going to stop only for I from 1 to 2. So let's say initially I is 1. So it says swap number 1. So we're going to swap this 2. What is A that, well, A that length is 5. Okay. And I is 1 minus 1, so this is 0 initially. So basically you have 5 as the result of this expression initially. When I is 1, this is going to be 5. So it is saying swap 2 and 9. Swap the first and last element. Okay, so we're going to have 9 here, and at the other end we're going to have 2. Then go back and increment I to 2. Okay, so I is 2. We're going to swap the second element. The question is swap it with what? Okay, so let's see. A that length is 5. Okay, I is 2. And 2 minus 1 is 1. So basically you are saying minus 1. And 5 minus 1 is 4. And this is the fourth element. So basically you're going to swap number 2 with number 4. In other words, we're going to have 3 here, and we're going to have 7 here. Okay, we didn't touch the element number 3. It remained where it is. Okay, the question is, what have we done? If you observe, basically we are reversing the elements in the array. Instead of 2, 7, 1, 3, 9, we now have 9, 3, 1, 7, 2. Okay, this is basically the idea of what the second algorithm is doing. But the point is not the algorithm or what it is doing. The question is, can you notice how we are representing this algorithm using pseudocode? What and what can you notice? I try to summarize the main points here. Okay, say notes on the pseudocode used in this course and also used in the book. First of all, we assume that array indices start from 1, not from 0. Okay, if you notice in both examples here, we assume the first element is at 1, which we initialize to be the key. Similarly here, we start our loop from 1 until length over 2, or floor of length over 2. We didn't start from 0. This is because throughout this course, we're going to assume that array indexing starts from 1. More natural to think of it from 1 than from 0. Okay, so from 1 to length, not from 0 to length minus 1. This is point number 1. Point number 2 is we can use shortcuts for simple functions such as swap. And you don't have to go and implement swap within your algorithm. You can assume that there is another algorithm called swap, or another function that you can call. Okay, this is to make the pseudocode simpler. Okay, another point is, and this is very important, indentation is used to indicate a block. Okay, a block for loops, a block for if-else, and so on. A block for the procedure itself. Indentation is used. We don't use braces to, as we used to do in Java. We use braces to beginning braces and closing braces to indicate a block. We don't do that in this course. Rather, we use indentation. If you have learned about a Python programming language, this is actually what it uses. It doesn't have any brace for beginning of a block. So if you go back again to the two examples, you can see here the routine here, everything inside it is shifted by some space. Okay, and also when you come to the for loop, all the statements inside it are shifted by some space. So this is to indicate that this is inside the for. Similarly, for the if, the statement inside it is indented by some spaces. So again, indicating this is within the if statement. You can see here, for example, this return is neither part of the if nor part of the loop. It's in the same level as the for loop. So it is just the next statement inside the routine itself. Okay, so this is very important. We don't use a block. We don't use braces to indicate the beginning and end of blocks. Rather, we use indentation. Okay. Next point is that variables such as I, J, key are going to be assumed to be local to the procedure that you are trying to represent as your algorithm. We shall not use global variable without explicit indication. So anytime you see a variable being used, it is assumed to be a local variable to that routine. Also important to note that you don't have to define the type of the variable. You don't have to say int I. Just say I equal to something. Okay, no need to specify the type. Okay, as I'm sure you saw there. You can see again, just to go back, we just say key equal to a at 1. We didn't say int key or double key. No, just define the variable. Similarly here, no need to say for int I, just for I equal to 1 to the length over 2, or floor of length over 2. Okay, the other point to note is that loop control variables will retain their last values after exiting from the loop. We know in Java, for example, once you exit the loop, you will lose the value of the variable. This is why if you need it, you have to define it actually before the loop, so that it remains there for you after the loop. However, here we're going to assume the value remains. After the loop, we're going to assume that the value still exists. So again, going back, so this I, we're going to assume after the loop finishes, it's still there. The value is the last value that will be assigned to I will remain. It will not be lost. Okay, this is the point. Similarly here, the loop control variables are the loop you use in for loop, for example, for I equal to 1 and so on. So after the loop, I will have the last value assigned to it. Okay, usually the value that will make the loop to stop. For example, here, when we were assuming the array is of size 5, when I becomes 2, we were able to enter the loop to do the swap. Now I will be initialized to 3, but now we will exit the loop because we have gone beyond a.length over 2. And therefore the final value of I after exiting the loop will be 3. It is the value that makes the loop to stop because it no longer satisfies the condition of being less than or equal to this last limit here. Alright, I hope that's clear. So that's another point to note. And the last point to note is we're going to assume array to be an object, and that object has attribute like length. So if we say a.length, we will get the size of the array. Okay, yeah, we will assume similar thing when we come to linked lists and trees later in the course. They are going to be treated as objects and they have attributes. Okay, right, so that is about the pseudocode. When we write algorithms, we are expected to write them in this format, not using Java code, but using pseudocode as we saw in that example. Okay, the next aspect is showing you examples of how to prove an algorithm is correct. Okay, so it said to prove that an algorithm is correct, we often need to provide a rigorous formal proof. Okay, as we normally learn from mathematics, when a statement is made, you need to really formally show that that statement is correct. Now, this can be done using a number of mathematical techniques, such as proof by induction, or contradiction, or something called loop invariant. Okay, I'm going to take a couple of examples to show this idea, and we shall encounter a few more examples later in the course. So example number one, suppose we are asked to prove that the sum of two odd integers is even. If you add two odd integers, you're going to get even. How can we prove that? So here is how you may go about it. So it says here, by definition of odd, if the two integers n and m are odd, then we know that there exist some integers j and k respectively, such that n can be represented as 2 times j plus 1, and similarly m can be represented as 2 times some number k plus 1. Any odd number can be represented as another number times 2 plus 1. For example, if I give you 9, 9 is odd. Can we represent it as 2 times another number plus 1? Of course we can. 9 will be 2 times 4 plus 1. 2 times 4 is 8, plus 1 will give you 9. So if you take any number, any odd number, you can represent it as 2 times another integer plus 1. So we're going to assume our two numbers n and m can be represented like this. Now try to add n plus m and see. Are you going to get even? Okay. So it means if we now sum up m and n, we're going to have n plus m will be 2j plus 2k plus 1 plus 1. Obviously 1 plus 1 is also 2. So we're going to have 2j plus 2k plus 2. And you can see that 2 is common in all of this, so we can factor it out. So 2 into j plus k plus 1. Now, given that j and k are integers, if you add them and then add 1, you're going to get another integer. And therefore, you are able to represent n plus m as 2 times some integer number. Now, if you can represent a value as 2 times something, definitely that value must be even. Okay? Yeah, for example, if I give you 10, well, 10 can be represented as 2 times 5. Because what? Because 10 is even. Yeah. So this is basically how you can go about proving the statement that says If you add any two odd numbers, you're going to get an even number. Let us take another example using proof by induction. Proof by induction actually is one of the most common ways of proving that an algorithm is correct. I'm sure we know proof by induction from one of your discrete structure courses, but we're going to take it anyway. So a proof by induction is a proof technique for proving that a sequence of events is true. And it follows the following two main steps. First, it will prove that the base case is true. Okay, so prove that the starting case is true. Second, which is called the inductive case, consists of two parts. First part is to make a hypothesis or to make an assumption. So we're going to assume that the event is true for some value k or k minus 1. And then we're going to show that the next, based on this assumption or hypothesis, we're going to show that the next step, the next event is true. If this our hypothesis is true based on the value k or k minus 1, then the next step, if you assume k, then we're going to assume the next step is going to be k plus 1. Whereas if you assume k minus 1, then the next step is going to be k itself. So it's up to you which one you use. Usually, sometimes it's easier to choose k, but sometimes it's easier to also choose k minus 1, depending on the problem that you are trying to prove. So that's basically how it goes. First, you prove the base case is true. Then you make a hypothesis for a particular value of k, and then you show that assuming that hypothesis is true, then the next step after that will also be true. If you can prove that, then it is true for all values of k or n. So let's take an example. Suppose we want to prove that the sum of integers I from 1 to n can actually be summarized as this formula: n times n plus 1 over 2. We're going to prove this by induction. I'm sure this is a very popular formula that we all know. For example, prove the sum from 1 to 10, or let's say to 5 to make it easy. Okay, the sum of I from 1 to 5. Basically, this means 1 plus 2 plus 3 plus 4 plus 5. Okay, what is it? Clearly, this is another 5. And 1 plus 4 is also 5. And then we have another 5 here, so the answer should be 15. The question is, if you apply this formula, can you also get 15? So let us see. N is 5 basically. So 5 times 5 plus 1 is 6. Divide by 2. And clearly you can divide 6. 2 can go into 6 3 times. And 3 times 5 is 15. So we get the same answer whether we add them one by one or we use the formula. So the formula is true, but can we prove it formally? Can we give a formal proof that the formula is always true? So we're going to do this by induction. So first assume the starting point. Show that the starting point is true. Well, the starting point is if n is 1. So we are taking the sum from 1 to 1. Well, from 1 to 1, there's only one number, which is 1 itself. So the left side is going to be 1. The left-hand side from 1 to 1, summation from 1 to 1 is just the 1 itself. What about the right hand side? Well, if n is 1, then we'll have 1 times 1 plus 1, which is 2, divided by 2. So again, 2 will cancel 2, and you're going to have 1. So clearly, the formula will hold for n equal to 1. Alright, so let's go to the inductive case. Here we're going to assume that the formula is true for a certain n. So let us say that the formula is true when n is equal to k minus 1. Okay, so obviously if n equal to k minus 1, we are saying the sum for I from 1 until k minus 1 of I, according to our formula, it should be n. Okay, well, n is k minus 1, so k minus 1 times n plus 1. Well, if n is k minus 1, if you now add 1, you will have k, so times k over 2. So here, this is going to be our assumption. Suppose this formula is true, that the summation of I from 1 to k minus 1 is this. Can we now show that the summation from 1 to k would also be true? Okay, so if it is true for n equal to k minus 1, can you show that it is true for the next step? Well, the next step after k minus 1 will be k. Okay, so can we show that the summation for I from 1 to k will also be according to this formula? In other words, it's going to be k times k plus 1 over 2. This is the next step. So in the inductive step, we need to prove that summation of I for I from 1 to k is k times k plus 1 over 2. Okay, we're going to do this in the next slide. First of all, we know that summation of I from 1 to k, we can write it as k plus summation of I from 1 to k minus 1 of I. What am I saying? What I'm saying is, instead of saying 1 plus 2 plus 3 plus 4 plus 5, this is basically the summation from 1 to 5 of I. So I'm saying we can write this as 5 plus summation from 1 to 4 of I. This is summation from 1 to 4 of I. Okay, which is k minus 1 in this case. So that plus 5 plus the k, the last element, the two will be the same, isn't it? Okay, so assuming that is true, from the hypothesis we know what is this. Okay, just to show you from the previous slide, the hypothesis says the summation of I from 1 to k minus 1 is k minus 1 times k over 2. So let us substitute this instead of this formula, instead of this summation, let us put this formula. Okay, so that's what we are doing here. Instead of this summation, we are replacing it with the formula that we assume from our assumption step. K minus 1 times k over 2. And now let's try to add these two terms. Well, this is a whole number and this is a fraction. For us to be able to add them, we have to change this to a fraction as well of the same denominator. So all you have to do is multiply top and bottom up by 2. Obviously, k alone can be assumed to be k over 1. Any whole number can be regarded as a fraction over 1. So now multiply top and bottom by 2. By 2 by 2. Then you will have 2k at the top and 2 at the bottom. Alright, so that means we have now two fractions of the same denominator 2, so we can just add the numerators. So 2k plus k minus 1 times k. Well, if you expand this is k squared minus k. Okay, so you have k squared. Now 2k minus k will just be k. So you have k squared plus k over 2. And you can factor out the k since k is common. So if you factor out the k, you are left with k plus 1 all over 2. And this is actually what we wanted to prove. We want to prove the summation of I from 1 to k is in fact k times k plus 1 over 2. So that shows that the formula is always true. We have proved it by induction.